Hey y'all, I hope everyone's doing well. Let's spend a little bit of time talking about chapter 31. Now, this chapter in the textbook is kind of like this guy's magnum opus or something. And he's spent a lot of time talking about some really important processes, but maybe it's at a depth that might be a little much for us. So I'm going to try to keep this as simple as possible. We're going to focus on the three essential domains of processing, and then we're going to look at two special ways that this processing functions uniquely in X-ray. Okay, so here's some learning objectives for us. First of all, we're going to be defining spatial, intensity, and frequency domains. So the three domains that he talks about in the text. And these are ways of sorting information, but they're almost like different worlds. So we'll talk about that metaphor. We'll list examples of each that are hardwired back to clinical practice. Then we're going to discuss use of gradient processing, and particularly this is where we apply the histogram analysis information and how it relates to lookup tables to customize image brightness and contrast based on the anatomy of interest. And finally, we're going to look at Fourier transformations, which don't run screaming out of this YouTube video. We're going to try to keep these as simple as possible. They are fairly complicated mathematical equations, but we're going to look just at how they function specifically towards edge enhancement in radiography. So when we're thinking about digital processing domains, I really like the metaphor that he comes up with in the textbook on page 497, that these are really like different worlds. And so I selected this MC Escher print of the three worlds, and we're going to be looking at this print in different ways to use different processing domains to process this as a way to see better details. Like within the three worlds of this domain, we have, I guess in the world of MC Escher, we have the world of the earth, right, where the trees are growing, the world of the air, which is, where the leaves have fallen through the air and landed on the world of the water. But for our purposes, the ways that this information is sorted differently is spatial domain. And so in the painting here, the spatial domain is the ways that, for example, the trees relate to the fish. They're more north on the picture than the fish, and the fish is at the bottom of the picture. And so when this image was digitized, those things were spatially located that way. The intensity domains are ways of sorting values of gray level, which are stored in every pixel of value. So for example, there's different intensity on the leaves. They're more white than the trees. They're, of course, more black. They're in a different domain in terms of their intensity. And finally, maybe the hardest one to wrap our minds around is going to be the frequency domain. And this is loosely related to the size of objects. It has to do with low and high frequency signals. So that one's going to be the most difficult one to unpack, so I'll save it for just a minute. Let's talk first about the spatial domains. You know what? Every single one of these you've done, if you've ever done anything like Instagram or whatever, edited an image online, you have used one form of a spatial domain operation, I guarantee it. So the three broad classifications are point processing, or these are things that are done point for point. And a good example of that is subtraction. So here on the right is an image, the original, and I've subtracted away the portion that has the fish on it, and I did that point for point. Every single point that was in that lower section, I subtracted away. Area processing is when we select an area and we reassign values based on location. And a good example of this is zooming. So if I were to zoom in on the fish now, this is a form of area processing. So in this instance, there's a subsection of the image that I've selected, and within that local area, the value that was contained in every single pixel is going to be reassigned to maybe a group of 4 pixels or a group of 9 pixels. And so the effect is that every single pixel is combined to form larger pixels that contain a single value, and that in essence brings us closer into this field of view. And so we'll call that area processing. Now I'm going to area process out, right? For our last way of thinking about, which is global processing, and this is massive spatial operations that occur across an entire image. And so this is like figure 498 in our textbook, figure 31-1. Every single, oh, and my picture got reflipped. I wonder who did that. That's interesting. Okay, so initially this image was flipped on my PowerPoint, and I can show you the PowerPoint if you're curious about it. But some part of this computer process has histogram corrected this. Initially, I had it flipped so where the fish was looking off in a different direction, and this is not image translation. This is a one-to-one replication of the exact same image. But if you can imagine that this image had been flipped over its y-axis right here, so that everything's on this side and the other side, we would call that image translation. So imagine that, if you will. I'm not sure how that changed. So the intensity domain is that regardless of location, the pixels are sorted based on their individual values. So by individual value, I mean their gray value, or whether they're white or whether they're black. And so a really good example of this that we've already explored in this class is histogram analysis. That is essentially resorting things based on their intensity. And gradient process is going to further use information in a lookup table to customize grayscale based on the specified anatomy. Now that's really interesting, because what that's saying is that every chest x-ray has a certain range of grayscale values that looks like every other pixel, every other chest x-ray. So we can use that information to enhance contrast or to kind of normalize images. Now the way that the computer does that is using intensity transformations, and it will either compare the histogram like we've learned about to other histograms and make changes on the histogram itself by either subtracting or zooming in on a volume of interest, or it could say, you know, all of these different histograms that we've produced of chest x-rays are going to be better if we change the intensity kind of across the board. And so that's what he's talking about in the textbook when he talks about gamma changes. So these gamma transformations, and I want to zoom in because it is interesting to look at what's happening when we do a change in the contrast versus the change in the gamma. So with the increased contrast, we've lost some of the fine detail of the leaves, like in this area right here. We can't see the veins on those leaves. But with the increased gamma, we have, but conversely, we've also lost some of the fish. So the gamma can be used very much like windowing and leveling in the textbook, but it's very much tied back to a certain set of lines that the computer is going to process the information based on, and that's what we're talking about when we talk about lookup table values based on gamma. So let's change the slide and look at that. Now I really like this illustration from our textbook. It's found on page 504, and you know what, you're probably going to see it again. So let's talk about why this image is so important. First of all, it does show us a dynamic range, which is a number of gray levels represented on the image, and in this case it's everything from here to here. That's all that we could potentially represent on these various images. Now, how that dynamic range is manifest on the image for the viewer changes based on the slope of the line. So like the steep slope, like slope L, is a very high contrast gradient. So that would be something that we might apply to a low subject contrast piece of anatomy, like for example an abdomen. The shallow slope represents a low contrast gradient, and so like slope A or slope E have a more shallow slope. They're not as steep as slope L, and so those are something that we might apply to, again, conversely, a high contrast piece of subject anatomy in order to lower the contrast, because they're going to give us a lower image contrast. Now the right to left portion of the curve, so we could move any one of these curves, like we could shift L this way or we could shift it that way. That would change the brightness level of the image. So if you can imagine, anytime we're manipulating the window and level, we are essentially changing kind of the shape of these curves in the way that the computer's processing the data. Now, one difficulty with any of these changes is that we could potentially wind up clipping out a portion of the curve. If there's any part of the curve that falls outside of the range of gray levels or the bit depth that any one pixel can process through, then we would essentially be losing data. So think about the image that's too dark, or the image that doesn't have all the information that we want on it. What's happened in that instance is I would encourage you to look at page 506, figure 3111 in the textbook, he shows how this kind of data clipping could occur. And one last thing to really stress, and this is something that I really can't say enough in this class, but page 507, absent details, like if the anatomy is underpenetrated, we didn't get enough x-rays through to actually have information to sort, we can never recover that. We can't do any amount of gradient processing to recover information that's not there. Okay, the last domain that we really should talk about is the frequency domain. And I don't know if you noticed when I shifted to this new slide, it processed kind of funny, like it started out kind of fuzzy and then all of a sudden it got sharper and sharper. Well, interestingly enough, that's in part because the information is being processed in the frequency domain. So what a frequency domain does is it does operations where it breaks images into wave components. We can think about it just like the wave frequency formulas that we use when we're talking about electromagnetic spectrum and stuff like that. So a large object is going to have long wavelengths and low frequency. So if you think about a large object is like a low energy object. A small object is going to have a short wavelength and high frequency, and so we can think about it as being like a high energy object. Now this is really, really helpful actually to think about things that way. So for example, the small object of the fish's eye on this image over here has a high frequency. And that means there's a high frequency of detail in the fish's eye or the scales on the fish's back. Versus the large objects, the things like the dark black hues and things like that have a very low frequency. So we can actually break these different waveforms. We can take these complex waveforms here and we can process them out into their individual parts, right? And so he talks about this very elegantly in the textbook. Let me get a page number for us real quick. But I'm going to zoom in on this. It gets page 517. And this is very interesting if you think about it. I don't want us to get lost in this too much. But this sine wave, this complex waveform here on the left, has been processed out through Fourier transformation into all these different component wavelengths. And this is actually read as a single wave, even though it's all these different component wavelengths. So if one is going up and the other is going down, they kind of cancel each other out, and they form this waveform here on the left. So we've in essence decomposed this or transformed it into all of its component parts. And that's one way to think about what a Fourier transformation is doing. And you might be asking, why is that helpful? Like, what possible purpose does this serve? Well, what's interesting is that we can use this to choose which waveforms we want to sample to be in our image. So for example, say we don't like this waveform down here on the bottom, we can subtract it out, we can get rid of it. And that's exactly what we're doing when we do edge enhancement. So you can see, if you look between the image of the fish on the left and the image on the right, there's a lot more detail, particularly in the scales on its back. The edges are really popping on this image on the right. Now, what's also interesting to observe on this image on the right is that we also have more image noise. The image is more modeled, it's more grainy looking. It has kind of almost a texture to it. And that's because anytime we enhance an edge, we will also enhance the noise that is there latent in the image. So as the computer selects out which waves to add back into the processed image, we do what we call a pyramid decomposition, and we can use that to extract out or suppress the noisy waves and boost the signals that we actually want. But again, to reiterate, anytime we're doing edge enhancement, we'll also enhance the noise, at least with a Fourier transformation. Now you might be wondering, what on earth is all this about? Well, interestingly enough, this is exactly how filter back projection works in CT scanning. So not only is this used for edge enhancement in radiography, this is also how filter back projection works to produce CT images. It goes through a number of Fourier transformations in order to produce the image. And interestingly enough, it's also a big part of how calculations are done for dosimetry in radiation therapy. So all of these frequency domain process, they're important. I would use it as a review of understanding that if a long wavelength, it has a low frequency, short wavelength have high frequency, and so we can sort out these different frequencies as a way to increase edges, but it also kind of manages to mess with our noise. Well, that's it. Hopefully that was helpful. I appreciate your emails and any questions you might have about this. I'm going to post a learning activity related to this too. But the last thing I'll leave you with is one of my favorite Simpsons intro routines is them walking through an MC Escher painting to their couch. Bye.